So when you have a state change, you're going to also have an entropy change. Here we're looking at solid water, ice, changing to liquid water, and then into the gas phase. And what happens is the amount of disorder possible increases. In a solid, all the particles are arranged in a particular order. There's a crystalline structure. They're all fixed relative to each other. In the liquid state now, those particles are able to move around, and so that increases the amount of entropy. Here, the particles are still able to move around, but now they're also able to expand away from each other. Here, they had to stay touchingly close, but now they can expand into whatever space is available. So, the easier way to think of it is to say, well, the gas state's more disordered than the liquid state. The formal way of saying that is there's more energetically equivalent ways of arranging the particles in the gas state, and so the entropy is larger. If that's looking at just the particles moving around, but if we just look at the particles themselves, in a solid we've just got vibration. So these solid particles are vibrating because, as we learned, matter is always moving. It would only be still at 0 Kelvin. So, the molecules in this desk are moving. We can't see them, but they're just vibrating in place, right? So there's movement here, and so these have energy, but they just have the vibrations. So if we get into the gas state, now we also have rotational energy, so it can spin, and also translational energy. It can move from one place to another. So there's different places, there's more places for the energy to be put, and therefore more microstates. Any questions about that? So you go from a solid to a liquid, from a solid to a gas, from a liquid to a gas, the entropy will increase. And so this is something that you should remember, okay? And it's not too hard if you think about disorder, right? A gas is more disordered than a solid. So when you go up that transition chain, you're going to have an increase in entropy. So phase changes are going to cause an increase in entropy, or can. The other thing that will happen is if we have an increase in the number of moles of a gas during a chemical reaction, that will cause a net increase in entropy. Yeah? Pardon me? Right. So this is looking at the entropy of the system, yes. You can have a negative entropy change for the system if you have a larger positive change for the universe, for the surroundings. So we should be able to predict the change in entropy for each of these processes. And again, we're just looking at the system. So water boiling, is that going to result in an increase or decrease in entropy? Increase, because you have a state change, right? So this is positive delta S. Going from iodine in the gas state to iodine in the solid state. That's going to be negative because it's becoming more ordered. And then here we've got solid calcium carbonate going to solid calcium oxide and carbon dioxide. That's an increase because we've got more moles of gas. So that's the sort of stuff you need to be able to do with what we just talked about. Any questions? So any change in state will be accompanied by an exchange of heat between the system and the surroundings. Entropy is related to the distribution of energy among the particles that compose matter. So we can look at the change in entropy for the system, delta S, in reference to the quantity of heat exchanged with the surroundings at a constant temperature. Here, Q, this heat is the heat exchanged in a reversible process. We'll talk about that in a minute. And T, the temperature, has to be in kelvins. If we allowed Celsius, then this could be 0 and we'd have an undefined quantity, right? So temperature has to be in kelvins. So that gives us the units then. This is joules and this is Kelvin, right? So now this unit of joules per Kelvin makes a little more sense. So entropy is a measure of energy dispersal per unit of temperature. So when a substance, let's think about an ice cube because it's familiar. Ice cube melts, it's absorbing energy from the surroundings, right? That energy becomes dispersed into the system, and the entropy of the system increases because energy has been dispersed. Any questions about that? Entropy is a hard one to think about. Okay, what do we mean by a reversible process? Reversible process is one where the direction of the process will change based on a very tiny and infinitesimally small change in some property. So an example is ice melting at 0 degrees Celsius. So that is the melting freezing point of water. So at 0 degrees Celsius, you're going to have ice and water present both. If we make just a very small change in the temperature, just take out a tiny bit of energy, that's going to tip it and it will be freezing. If we increase it, the temperature, just a tiny bit, then it will go in the other direction. So that's a reversible process. If we think about an ice cube melting on a countertop at room temperature, that is not a reversible process. So we've got an ice cube on the counter, it's maybe 72 degrees in here, you turn the thermostat down to 70. Does it start freezing? No, it doesn't. Removing a small amount of heat will not change the direction. So reversible processes are in a constant state of equilibrium. They're highly idealized, meaning most processes that you can think of are not reversible processes. These are almost imaginary things. Okay, let's calculate the change in entropy that occurs in the system when 10 grams of acetone vaporizes from a liquid to a gas at its normal boiling point. And they give us the heat of vaporization. So the equation that we had was delta S is Q reversible divided by the temperature. So here we have liquid acetone vaporizing at the boiling point. So this would be a reversible process. Well, the temperature is pretty easy to figure out. This is the temperature, right? But we need that to be in Kelvin. So we'll convert that to Kelvin. .329.25 Kelvin. Okay, so there's T. What's Q? Well, Q is the energy change. Under many conditions, the heat exchanged is equal to delta H, given that there aren't other complicating things going on. So we're going to use delta H as Q. So this is 29.1 kilojoules per mole divided by the temperature. Well, is that going to give us the right units? No. I mean, we got the kilojoules. We can fix that. We got moles in here. So, let's back up a minute. Q depends on how much stuff is reacting or changing, right? So we can't just equate Q and H. Yes? Yeah. So what we need to do is we need to convert 10 grams of acetone to moles, and we'll take this delta H in kilojoules per mole, we'll multiply by the number of moles. So 10 grams of acetone, we need to convert that to moles, and then we're going to get to kilojoules. Delta H was 29.1 kilojoules per mole. So this would give us kilojoules, but the units of S are joules. So we'll need to add one more term here and convert to joules. So 10 divided by 58 times 29.1 times 1,000. And that would be joules. Did I do that right? My brain is really not so great right now. So what we want up here then is we want the amount of heat transferred for this particular amount of thing happening. So 5,000, 10.5 joules. So we take that and divide by the temperature. (15.2) joules per Kelvin. Any question? Again, you need to watch out for the kilojoules here. Delta H is almost always going to be in kilojoules because delta H is usually a fairly big number. Entropy is always going to be in joules because it's a small number. And so that's something that can mess you up in your calculations. You can get everything set up right, but if you don't convert this to joules, you're going to come up with the wrong answer. So just watch out for that.